Data are either categorical or quantitative. Categorical data are often referred to as qualitative data because the data can be grouped in categories. Each element has an attribute or quality. Categorical data has either nominal or ordinal scale and can be either numeric or non-numeric. Statistical analyses are limited to frequency tables, bar charts, and pie charts. A frequency distribution is a tabular summary of data showing the frequency or number of items in each of several non-overlapping classes. The objective is to provide insights about the data that cannot be quickly obtained by looking only at the original data. The Murata-N example here shows the results of a sample of 20 guest responses to the hotel's customer survey. The survey asked customers to rate Murata's quality as being excellent, above average, average, below average, or poor. Three customers surveyed said Murata's quality was below average. 9 customers surveyed said Murata's quality was above average. 5 customers surveyed said Murata's quality was average. 2 customers surveyed said Murata's quality was poor. 1 customer said Murata's quality was excellent. The numbers in non-overlapping classes, excellent, above average, average, below average, or poor, are called frequencies. The frequencies of customers saying Murata's quality was poor is 2. The frequency of customers saying Murata's quality was below average is 3. The frequency of customers saying Murata's quality was average is 5. The frequency of customers saying Murata's quality was above average is 9. The frequency of customers saying Murata's quality was excellent is 1. Frequencies add up to the number of customers in a sample, which is 20. The relative frequency of a class is the fraction or proportion of the total number of data items belonging to the class. Since 2 people rated Murata's quality as poor, the relative frequency of customers saying Murata's quality was poor is found by dividing 2 by 20. The relative frequency of customers saying Murata's quality is poor is 0.1. Since 3 people rated Murata's quality as being below average, the relative frequency of customers saying Murata's quality was below average is found by dividing 3 by 20. The relative frequency of customers saying Murata's quality was below average is 0.15. Since 5 people rated Murata's quality as average, the relative frequency of customers saying Murata's quality was average is found by dividing 5 by 20. The relative frequency of customers saying Murata's quality was average is 0.25. Since 9 people rated Murata's quality as above average, the relative frequency of customers saying Murata's quality was above average is found by dividing 9 by 20. The relative frequency of customers saying Murata's quality was above average is 0.45. Since 1 person rated Murata's quality as excellent, the relative frequency of customers saying Murata's quality was excellent is found by dividing 1 by 20. The relative frequency of customers saying Murata's quality was excellent is 0.05. The relative frequency distribution is a tabular summary of a set of data showing the relative frequency for each class. The sum of relative frequencies equals 1. Percent frequencies are found by multiplying relative frequencies by 100, and they sum up to 100. Bar charts can use frequencies, relative frequencies, or percent frequencies. Since the y-axis on the one labeled below is labeled frequency, we want to construct a bar graph for the frequency of a customer ratings at Murata-N. Since the frequency of customers saying Murata's quality was poor is equal to 2, the bar for this category stops at 2. Since the frequency of customers saying Murata quality was below average is 3, the bar for this category stops at 3. Since the frequency of customers saying Murata's quality was average is 5, the bar for this category stops at 5. Since the frequency of customers saying Murata's quality was above average is 9, the bar for this category stops at 9. Because the frequency of customers saying Murata's quality was excellent is equal to 1, the bar for this category stops at 1. Notice there are gaps in between the bars. This is not the case when the variable has interval or ratio scale. The pie chart is commonly used as a graphical device for presenting relative or percent frequency distributions for qualitative data. You begin by first drawing a circle. The relative frequencies are used to divide the circle into sectors that correspond to the relative frequency for each class. The above average class has a relative frequency of 0.45, so it consumes nearly half of the circle. The average class has a relative frequency of 0.25, so it consumes a quarter of the circle. The below average class has a relative frequency of 0.15, so it consumes less than a quarter of the circle. The poor class has a relative frequency of 0.1, so its slice of the pie is slightly less than the slice corresponding to below average class. The excellent class has a relative frequency of 0.05, so it consumes the remaining part of the circle that should be smaller than the slice corresponding to poor class. The pie chart imparts information in an efficient and compact manner. Insights gained from the Murata N pie chart includes: 1/2 of customers surveyed gave Murata a quality rating of above average or excellent. Now this should please the manager. On the other hand, for each customer who gave the hotel an excellent rating, there were 2 customers who gave the hotel a poor rating. This should not be well received by the manager. Recall from Chapter 1 that quantitative data uses numeric values to indicate how much or how many. Quantitative data can be discrete or continuous. The number of cans of Coca-Cola sold by the gas station near your house is an example of a discrete variable. The volume of gasoline sold by the same gas station is an example of a continuous variable. Quantitative data is always numeric, and so arithmetic operations, multiplication, addition, subtraction, are meaningful. Statistical analyses not only include frequency tables, bar charts, and pie charts, but also averages, standard deviations, and correlations. In Chapter 1, we constructed a histogram and computed the sample mean for the Hudson Auto Repair example. If you recall, the manager of the garage wanted to compile statistical summaries of several variables associated with the operation of her garage. One of the variables of interest is the cost of parts used in tune-ups. She randomly selected 50 tune-up invoices. She entered the cost of parts, rounded to the nearest integer, into an Excel spreadsheet like the data shown below. Sorting the data from the minimum value of 52 to the maximum value of 109 is helpful in understanding how medians, modes, and percentiles are found. In the previous chapter, we chose intervals with a width of 10. Well, how do we come up with this? First, you decide how many classes you need, and then determine the class width. Typically, you want between 5 and 20 classes. Classes are sometimes referred to as intervals. Excel refers to them as bins and categories. The larger your data set, the more classes you generally need. For smaller data sets of, say, size 25 to 30, you use 5 classes. The goal of choosing the number of classes is to get a good idea of what the distribution might look like. Next, you must decide how wide each interval should be. The following guidelines for selecting class width represent a rule of thumb. Pick 9 numbers nice numbers like 5, 10, 25, 50, 100, etc. First and foremost, use class widths of equal width. The approximate class width is found by subtracting the minimum from the maximum value and then dividing this difference by the number of classes you want. We chose 6 classes in the previous video for our Hudson Auto Repair data, whose minimum and maximum values were 52 and 109. So the class width according to this equation is 9.5. Well, this isn't a nice number. We chose instead the number 10 because it is nice. So 10 was our class width. Since the smallest value is near the nice number of 50, and our class width is 10, our first interval is 50 to 59. Although the difference of the two numbers is 9, there are 10 numbers from 50 to 59. Because this data is discrete, remember, the owner of the repair shop rounded the dollar values to the nearest dollar. The first interval, 50 to 59, contains 2 invoices. Hence, the frequency or count in this interval is 2. The second interval, 60 to 69, contains 13 invoices. Hence, the frequency of this interval is 13. The third interval, 70 to 79, contains 16 invoices. Hence, the frequency of this interval is 16. The fourth interval, 80 to 89, contains 7 invoices. The frequency of this interval is 7. The fifth interval, 90 to 99, contains 7 invoices. The frequency of this interval is 7. The sixth and final interval, 100 to 109, contains 5 invoices. The frequency of this interval is 5. Notice that the minimum of 52 and the maximum, they're in their respective intervals. The frequencies in the intervals 50 to 59, 60 to 69, 70 to 79, 80 to 89, 90 to 99, and 100 to 109 are 2, 13, 16, 7, 7, and 5. These sum to the sample size of 50. The relative frequency of a class is the fraction or proportion of the total number of data items belonging to the class, in this case, interval. Since the frequency of invoices between 50 and 59 is 2, the relative frequency of this interval is found by dividing 2 by 50. The relative frequency of this interval is 0.04. 2 divided by 50 is 0.04. Since the frequency of the invoice between 60 and 69 is 13, the relative frequency is found by dividing 13 by 50. So the relative frequency is 0.26. The frequency of invoices between 70 and 79 is 16. The relative frequency of this interval is found by dividing 16 by 50, which is 0.32. The frequency of invoices between 80 and 89 is 7. The relative frequency of this interval is found by dividing 7 by 50, or 0.14. The frequency of invoice between 90 and 99 is 7. The relative frequency of this interval is found by dividing 7 by 50, which is 0.14. The frequency of invoice between 100 and 109 is 5. The relative frequency of this interval is found by dividing 5 by 50. So the relative frequency of the last interval is 0.1. The sum of relative frequencies is always 1. The sum of frequencies is always n, in this case 50. The percent frequency of interval 50 to 59 is found by multiplying the relative frequency, 0.04, by 100, which is 4%. The percent frequency of interval 60 to 69 is 0.6%. The percent frequency of interval 70 to 79 is 32%. The percent frequency of interval 80 to 89 is 14%. The percent frequency of interval 90 to 99 is 14%. The percent frequency of interval 100 to 109 is 10%. the sum of percent frequencies always equals 100%. Histogram is a bar graph, but a bar graph is not necessarily a histogram. The bars of a histogram have no gaps between them, and their widths are equal to the width of the intervals used in the frequency table. If percent frequencies are used, the histogram is a percent frequency histogram. In this diagram below, the y-axis says frequency. So we're going to construct a frequency histogram. Since the frequency of interval 50 to 59 is 2, the bar corresponding to this interval stops at 2. Since the frequency of interval 60 to 69 is 13, the bar corresponding to this interval stops at 13. Since the frequency of interval 70 to 79 is 16, the bar corresponding to this interval stops at 16. The frequency of interval 80 to 89 is 7. The bar corresponding to this interval stops at 7. The frequency of interval 90 to 99 is 7. The bar corresponding to this interval stops at 7. The frequency of interval 100 to 109 is 5. The bar corresponding to this interval stops at 5. The area, the total area of the red bars is 50. If this were a percent frequency histogram, the red bars would have an area equal to 100%. If this were a relative frequency histogram, the red bars would have an area equal to 1. Now the histogram estimates a true distribution of tune-up parts cost. In most cases, we won't know the true distribution of this variable. The area under the true distribution is equal to 1. For the same reason, the bars of a relative frequency histogram have an area equal to 1. The histogram suggests the data is positively skewed, or skewed right, since the right tail, the bars corresponding to intervals 80 to 110, is longer than the left one, the bar corresponding to interval 50 to 59. A histogram graph using data from a sample drawn from a symmetric distribution, heights and weights of people, will be symmetric with a skew equal to 0. Note, the mean and skew are sample statistics if computed from sample data. When skew equals 0, the left tail is a mirror image of the right tail. A histogram graph using data from a sample drawn from a distribution that is moderately skewed left will have a tail, left tail, that is slightly longer than its right tail. When the left tail is slightly longer than the right one, the skew is close to 0, but negative. A histogram graph using data from a sample drawn from a distribution that is moderately skewed right will have a right tail slightly longer than its left one. When the right tail is slightly longer than the left one, the skew is close to 0, but positive. A histogram graph using data from a sample drawn from a distribution that is heavily skewed right will have a right tail much longer than its left one. When the right tail is much longer than the left one, the skew is positive and large. The cumulative frequency distribution shows a number of items with values less than or equal to the upper limit of each class. The cumulative frequency of interval 50 to 59 is the frequency of invoices with parts costing at most $59, which equals 2. The cumulative frequency of interval 60 to 69 is the frequency of invoices with parts costing at most $69. Since there are 2 invoices between 50 and 59 and 13 invoices between 60 and 69, the cumulative frequency is 15. The cumulative frequency of interval 70 to 79 is the frequency of invoices with parts costing at most $79. Since there are 2 invoices between 50 and 59, 13 invoices between 60 and 69, and 16 between 70 and 79, the cumulative frequency of this interval is 31. The cumulative frequency of interval 80 to 89 is the frequency of invoices with parts costing at most $89. Since there are 2 between 50 and 59, 13 between 60 and 69, 16 between 70 and 79, and 7 between 80 and 89, the cumulative frequency of this interval is 38. The cumulative frequency of interval 90-99 is the frequency of invoices with parts costing at most $99. There are 2 between 50 and 59, 13 between 60 and 69, 16 between 70 and 79, 7 between 80 and 89, and 7 between 90 and 99. The cumulative frequency of this interval is 45. The cumulative frequency of the final interval is always equal to the sample size, which is 50. The cumulative relative frequency distribution shows a proportion of items with values less than or equal to the upper limit of each class. All the cumulative relative frequencies are between 0 and 1. Since the cumulative relative frequency of invoices with parts costing at most $59 is 2, the cumulative relative frequency of this interval is found by dividing 2 by 50, which is 0.04. The cumulative frequency of invoices with parts costing at most $69 is 15. The cumulative relative frequency of this interval is found by dividing 15 by 50, which is 0.30. The cumulative frequency of invoices with parts costing at most $79 is 31. The cumulative relative frequency of this interval is found by dividing 31 by 50, which is 62, or 0.62. Since the cumulative relative frequency of invoices with parts costing at most $89 is 38, the cumulative relative frequency of this interval is found by dividing 38 by 50, which is 0.76. The cumulative frequency of invoices with parts costing at most $99 is 45. The cumulative relative frequency of this interval is found by dividing 45 by 50, which is 0.90. Since the cumulative frequency of invoices with parts costing at most $109 is 50, the cumulative relative frequency of this interval is found by dividing 50 by 50, which is 1. The cumulative relative frequency of this interval is 1 and is always 1 because it is the final interval. And the final interval of any cumulative relative frequency is always equal to 1. The cumulative percent frequency distribution shows a percentage of items with values less than or equal to the upper limit of each class. Multiplying all the cumulative relative frequencies by 100 yields cumulative percent frequencies. The cumulative percent frequencies are 4, 30, 62, 76, 90, and 100. The final cumulative percent frequency is always equal to 100%. An ogive is a graph of a cumulative distribution. On the y-axis, we could have cumulative percent frequency, or cumulative relative frequency. In the diagram here, the y-axis is labeled cumulative percent frequencies. Hence, this ogive is a cumulative percent frequency distribution. The percent of invoices with parts costing at most $59 is 4%. Now this is the same as saying the percent of invoices with parts costing less than 60 is 4%. Hence the height of 4% at the value 60. We can also say that the percent of invoices with parts costing less than $50 is 0%. So this ogive starts at $50 and 0%. Then travels to the point $60 and 4%. The ogive next travels to point $70 and 30%. Because the percent of invoices with parts costing at most 69 or less than 70 is 30%. Next, we go to point 62. Because the percent of invoices with parts costing at most $79 or less than 80 is 62%. Next we go to point 90 and 76. Because the percent of invoices with parts costing at most $89 or less than $90 is 62%. The percent of invoices with parts costing at most $99 or less than $100 is 90%. The percent of invoices with parts costing at most